Hey guys.
Hey there.
Hi, Professor.
Hey.
Yes. Last lecture that in the if and else that you say that we can only use once of them. Like, what do you mean that? Like that? Like, can I use multiple times for if or else, or I can use one of them?
You can
Like,
use multiple else ifs. So you can actually put as many else ifs as you want. But there can only be one else. There can only be one if. But if there's more conditions that you want to put into an if statement, you can put as many else ifs as you want. So oops.
so like example like if I can put like 2, 3 of them, but for the else at the end it's only one, right?
Right. Yeah, because the else is the else by itself is just the like the last resort kind of thing. So you can only have one last resort kind of thing, but you can have as many other conditions, else if conditions as you want.
Okay, I got it. Thank you.
Mm-hmm.
Professor, I had a question about the homework.
Sure. Mm-hmm.
Will you be going over any of the problems, or do we just go to your office hours?
I wasn't planning to, but I haven't received any questions on the homework so far. So usually the questions that I go over in the lectures, you can people usually ask then, and then I can take it. But if a lot of people are asking questions on the homework, then that's when I address it in the lecture. But you can ask right now, and we can go over it a little bit.
Let me open it up. I had issue on 3C, I think. Let me open it up.
Okay.
It's the one with else if,
Mm-hmm.
and yeah, the little long one.
Yeah. So this one is this one's interesting just because it's kind of it's supposed to be kind of similar to the example that we did kind of right before we signed off last time, which is like an if statement inside a for loop. But this is if, and else. And so the hint I'll give you here is that the if and else if conditions are for checking which rows in the matrix that you are. because if you kind of look at if you kind of examine each rows in the matrix right here, you can see that, for the second row, the third row, and the fourth row, they're all kind of the same in that they all have a single -2, and then they have 2 1s on the wings, right? And so there are 2 1s on both sides. But the first row here only has one of those, and the last row only has one of those 2. So, you should do something different depending on if you're in the first row, if you're on the middle 3 rows, or if you're on the last row. And so I think the thing that usually trips people up is, what the heck do you put down here? So like, why do I have this B outside of this if statement? And so this B right here is, this is for something that takes place on every single row. And so if you look at each row in the matrix, what is something that's consistent on every single row? Each one has a -2, right?
And yeah.
And the -2 is always in the same spot. So it's always in the diagonal slot.
Yeah.
Right. So that's what you would deal with down here. And then everything else here is, dealing with if you're on the first rows, the middle rows, or the last row. Yeah.
All right. Interesting. Okay. Thank you.
Mm-hmm.
Hey, Professor.
Hey, what's up?
Hey, I had a quick question. I know this may be a side note. This is just something I'm doing for work. I know this may probably be a silly question as well, but I know you can't run an FEA analysis on STL files. Because I ran it before in the SolidWorks simulation with the SolidWorks file. But do you know any like of any softwares that can convert an STL file to like a readable file, or like a file that actually has geometry for FEA analysis?
So how are you generating this STL file? Is it coming from SolidWorks?
So this STL file is generated from our own software in-house that our software developers made.
I see. Okay. Okay.
And then, so for example, I work in the aligner industry, so I have like Invisalign, but we're like competitors with them. So we have our own guys that, you know, take the scans, they send us the STL file.
Okay.
So yeah, I've been trying to figure out what package or what specific thing that we can use to convert it, because I want to run some FEA analysis on it and trying to convince the guys to buy some ANSYS or Altair.
I see. I see. Yeah, STL actually is pretty flexible. So I know a lot of softwares can read it. Can you not open it in SolidWorks?
No, you can open it in SolidWorks. It's just
Okay.
when I try to run the FEA simulation package in SolidWorks, because I just need to provide just to provide, hey, this is what an FEA report looks like, but you know, SolidWorks simulation isn't as accurate as the other packages.
Right. I mean, SolidWorks actually, you know, I've actually spent a good amount of my life kind of pooping on SolidWorks simulation, but I think it's actually not bad. So I mean, it's you know, if you can do it in SolidWorks, I think that's okay. But if you want to use it with ANSYS, I think the format that's used a lot is IGS or step file. And so I'm not sure if it can do this, but there's an open source software I use called ParaView. So I can actually show you the interface here. So it's spelled like this basically.
Oh, okay.
And so I use this to load. So I know ParaView for sure can read STLs. I don't, and usually I use ParaView to convert between STLs and some like other file formats that I use for my research. I haven't tried converting to STEP or IGS, but I think it's worth a try because ParaView does have a lot of formats on there.
Okay, maybe I can convince IT to buy this for us. Okay.
It's free. ParaView is
it's free.
Open source, so it's free. Yeah.
Okay, nice.
I'm a cheap ass, so then I like to use free softwares when I can.
No, that's perfect, man.
Yeah.
Okay.
Yeah, give that a try, and then you know, that would be my first place to look. Yeah.
Awesome. Thank you, Professor. Appreciate it.
Yep. Okay, it's 5:30, so let's go ahead and get started today. Good evening, everyone. How's everyone doing today?
So far, so good.
Last class of the day, so
good. Yeah, same here. So I actually teach at this time every day, which you know, which is nice in a way because it kind of ends my day. But I usually like to cook during this time, so I'm kind of sad this semester that I can't cook as much. Okay, so the plan for today is we had a little bit left over from our MATLAB review that we were started on Monday, and so I have a couple more examples, and we want to talk about plotting, and so that will take up hopefully, you know, maybe the first 15-20 minutes of class, and then after that we're going to start you know, talking about the theory of you know, really starting to get into the theory by talking about finite differences. Okay. And so one announcement I want to make before we start is that, remember, our first homework is due on Monday. So I know some people have been working on it because I've gotten a couple questions, but you know, make sure you finish that and turn that in on Monday. So remember, the homeworks for this class, I'm just grading it based on completion, but you know, still, you know, do your best to, you know, complete it well, because it's only going to help you out in the long run. Especially as we start doing more complex code and more complex things for the exams and stuff. Okay. Okay, so are there any questions on what we covered last time, or any questions on the homework that I can answer before we get started today? Okay. All right, so let's get back into it. And so on Monday, kind of where we left off, from showing the answer, is we were talking about for loops and if statements. And so I think we kind of left off with this example here where we showed how to put an if statement into a for loop and how this is traditionally used, right? And so just to kind of jog your memory here, for this example here, what we wanted to do is we wanted to fill this vector, this even vector here with values, but we only want to do it for the even numbered indices, okay? And so the way that we accomplished this was we wrote a for loop, and from this for loop we visited every single entry in the vector, and then we wrote an if statement here to check to see when we're at one of the even number indices, okay? And so what this will do is that as the for loop goes, it'll check to see if we're at an even number index. And so to do that, we use this mod function here, which took the index, we divided it by 2 in this case, and we check the remainder. And if that remainder is 0, then we know that we're at an even number. And if we are, then we can assign a value here. So in the end, we get something that's kind of a flip-floppy pattern here. So we go 0, and then 2, and then 0 and 4, and so on and so forth, okay? And so before, just to kind of help you guys out with the homeworks too, I wanted to do a couple more complicated examples just so you can kind of get more exposure to, different ways that you can combine these guys, okay? Because with programming, what I find is that the concepts and the syntax themselves by themselves are not that complicated. I think what's difficult about programming is actually like using it in applications. So that's why I try to write this review with as many examples as I could, because I think the more of these that you kind of are exposed to, and the more you kind of hear, at least my own logic on how I wrote these examples, I think that's one way to practice programming. The other way to practice programming is just to do it yourself, and you get kind of good at that, right? Okay, and so in this example here, we're going to start with an empty 5x5 matrix. And so the first line of code here is going to be zeros 5x5, okay? And so all 25 entries in this matrix can be 0. And what we want to do is we want to fill the matrix according to the following criteria, okay? And so in the first row, we're going to start with number 2, and then each entry after that in the first row is going to count up by 2 in each subsequent entry, okay? So the first row should read 2, 4, 6, 8, 10, okay? In the second row, we're going to start with the number 3, and we're going to count it by 3 in each subsequent entry, okay? So it's going to be 3, 6, 9, 12, 15, okay? And then in the third row, we start with 4, count up by 4. Fourth row, we start with 5, count up by 5. And in the fifth row, we start with 6 and count up by 6, okay? And so, looking at this problem right here, we can see that we're going to need to assign a value to every single entry in the matrix, right? And so we're not going to leave any value unassigned. So all the zeros here will be converted. And so since we need to visit every single entry in this matrix, this is a good candidate to use a nested for loop, right? And so we're going to have basically one for loop and another. Because if you remember from this example last time, we used this nested for loop to visit and assign every single entry in a matrix, okay? And so, when you have cases like this where you need to visit a lot of different, every single entry, a nested for loop is kind of the most compact way to do that, okay? And so that's kind of the first part. And this next part where, each loop we're basically, counting up by we're basically adding 1 both to the starting value and to the amount that we're counting up, means that we're going to do something different on every loop, okay? And so let's kind of see how this is implemented so we can, kind of pick this apart, okay? All right, and so the first thing is, you see that we created an empty zeros matrix, so 5x5, and then we have our nested for loop here. So we have one for loop that loops over the rows, and we have another for loop that loops over the columns, okay? And then inside this nested for loop, we have a line here where we're going to assign a value to our matrix, okay? And so this looks very similar to the example that we did previously. The only wrinkle that I threw in here is that, now this counting variable, which before, we just had this counting variable just simply count up by 1, we're going to count it up by something else besides that. Okay. And so if we compare this to, what we have up here, we can see that now count is going to be equal to count plus row index plus 1. Okay. And the key, the key part of this example here is I just want to show you guys how you can use the row index or the loop index here in kind of more creative ways. And so, we've seen how row index can be used as a way to access entries in a matrix or a vector, but you can actually use it in calculations too. Okay. And so in this case, what this line of code will do here is that, when we go to the next entry in the inner loop, we're going to be counting up by a different amount, right? And so let's take kind of the first iteration of this outer loop as an example. So on the first iteration of this outer loop, row index is going to be 1, right? And we know from the problem specs here that, on this first row, we're going to count up by 2 in each entry, okay? And so that means that each time that the inner loop iterates, count needs to increase its value by 2, okay? And so essentially what we want for the first iteration, count needs to increase by 2 on each inner loop iteration, okay? I should say this is for the first outer loop, okay? And so we basically need to have count is equal to count plus 2, right? And so that's different from here, where up here we just incremented by 1, okay? And so one way that we can accomplish this is we can actually use the row index, right? Because on the first iteration of the outer loop, row index is just going to be 1. And so we're going to have count is equal to count plus 1, which is 2, okay? So we couldn't just write plus 2 right here, because then, we wouldn't be able to satisfy the next row. Where in the next row, we need to count up by 3, right? And so, since, we notice from the problem spec here that each row, we're increasing the count up by 1, then we can use this row index here to, account for that, okay? Because when we put it in this form right here, we automatically kind of satisfy that criteria there for, counting up by 1 additional more on each row, okay? Because for the second row, row index is going to be 2. And so we're going to have count is equal to count plus 2 plus 1. And so we count up by 3, which is, what we have. Okay. All right. And so the last thing I want to highlight in this example here is, we have a line of code here that's within the outer loop, but outside and above the inner loop. Okay. And what this line of code right here will do is this resets the count variable each time the outer loop iterates. Okay. And so that has to do with kind of this part of the problem statement here. For each row, you can see we're starting with a different value. Okay. And so since we start with a different value on each one, we can't just retain the same count value that we did previously. We need to reset its value. And so that's what this guy does right here. And so before we enter the inner loop, we're going to reset the value of count such that, for each entry here, we start with the appropriate number. Okay. And so, this example right here, I wanted to just highlight just, creative ways that you can use the loop index, and also, one way that you can do what's called like a variable reset. Okay. All right. Any questions on this? Okay. Oh, I've uploaded this code up to Canvas as well, so you can have that too. So that code will basically just contain everything in here. Okay.
So, quick question. Sorry.
Yep. Mm-hmm.
So the first 4, how you have the counts.
Mm-hmm.
What you're saying is that before it goes on to the inner loop, the next for loop, it resets the counts.
Exactly right. And so we're using this equal sign here. So the equal sign, remember, is assignment. And so we're basically assigning a resetted value for count before we move on to the next row. Yeah.
Okay. I remember for the, can you go to the nested for loops?
Yeah. Mm-hmm.
What is it? So why did we have the count on the outside of the for loop compared to right now in the example how we have the count inside of the for loop?
Yeah, so here we have it both. So so we have it kind of on the inside and the outside. The reason we have it only on the inside of the inner loop here is because there was no need to reset its value here on each row. And so let's go back to, this is the output for this example right here. And so when we go through the first row, on the second row, there's no need to reset it to like 1 or 2 or something like that. So since, as when we start on the next row, we're just going to keep counting from where we are before.
Okay.
But in this example, we had to start with something because, if you look at the output here, it ends at 10 right here, but we don't want to start at 10 on the next row. We want to restart at 3. And so that's why we have to reset its value.
Counts. Oh, all right. I see it. Okay. Thank you.
Yeah. Any other questions on this example? Okay, so let's look at one more example here. So this example here is, how we can use if and else if inside of a for loop. Okay, so this is actually not that different from this example here, but there's a little bit more wrinkles to it. Okay, all right. And so this example will say we're going to start with an empty vector of 25 entries, and then what we're going to do is we're going to loop over each entry and then modify them according to the following criteria. Okay, and so first we say if the index is an odd number, then we change the value of the entry to 1. Okay. Next, we say if the index is a multiple of 4, then we're going to change the entry to 4. And then in all other cases, we change the value of the entry to 24. Okay. All right. So first thing you should notice here is that, first of all, we start out with an empty vector. So we start with the zeros function just like before. And we're going to use a loop to visit all the entries. Okay. And then, according to what the index is, we're going to do something different. So the fact that, the problem statement here has a bunch of ifs, that tells us we should also put some ifs in our program, right? And so you can see here in the solution here, we have a bunch of ifs that changes value, okay? So let's check the first condition first. So the first thing we should check to see is if the index is an odd number, okay? And so we're going to use almost the same, conditional that we used on the previous example, right? And so we're going to take the modulo. And so that, remember, that's division with remainder. And then we're going to modulate the index divided by 2. And if the remainder is 1, and so that tells us it's an odd number, then we're going to change the entry of that vector to 1, okay? Okay, and then the next thing we're going to check to see is if it's a multiple of 4. And so if it's a multiple of 4, then we do the modulo of the vector index divided by 4. And if the remainder is 0 after that, then we change the entry to 4, okay? And so that's the second condition. So since that's part of the same if statement, we use else if. And then for the last condition, which is in all other cases, then we change the entry to 24, okay? And so since this is kind of like the catch-all case, then we use an else statement here. So that's kind of what you see right there, okay? And here you see kind of the same solution and then kind of the results of that guy, okay?
What did you say mod was again, the description of it?
So mod is a function that you can use to compute the remainder. And so what mod will do is it'll take the number in the first parameter here, it'll divide it by the second parameter, and then it'll return you the remainder of that division. Yeah.
Okay. Thanks.
Yeah. So this is kind of almost like just a little bit of an extension of the example we ended with last time. Okay. Okay. So any questions on this? Okay. All right. And so that's 2 more examples for you guys to look at. So hopefully those will help you out for the homework too. And so the last thing I want to talk about in MATLAB is how to plot stuff. Okay. And so plotting, I personally think is one of the really nice features within MATLAB. It's being able to take a bunch of numbers and then put it in a visual plot, and to do it as easily as you can do it in MATLAB is really, really nice. And so languages like MATLAB and Python does this really well too. I think gives it a huge advantage over some of the more heavy duty languages like C++ or Fortran. Okay, and so the syntax for plotting is actually really simple. So first you have to declare a figure. And so, in this case, I gave the figure number 1. Okay. You can use any number in there, but I usually like to start at 1. And in programs where I have to make multiple figures, then I just, count up over there. So I go figure 1, figure 2, figure 3. Okay. And then after that, you just call the plot command. Okay. And then the plot command takes 2 arguments. And so the first argument here will be the vector that's going to be used as the basis for the x-axis. Okay. And so the horizontal axis values you would put there. And then the second entry is just the vector, which is going to correspond to your y values. Okay. And so in order for this to work, both x and y have to be the same length. And so if they're different lengths, then MATLAB will give you an error. And I think that's probably one of the more common errors that people get. But if they're the same length, then MATLAB will produce a plot for you. Okay. Okay. And so here's just a very simple example. So here I've created an x variable, or to be a vector, which is basically going to be a lin space. And so it's going to be evenly spaced between 0 and 5 with 100 entries. And then y is just going to be the square of that. So it's just going to be basically just a quadratic function. Okay. And so, from this, we're going to, now that we define our vectors, we just plot it. And then we can define a title and label our axes using these functions right here. And then here we have our plot. Okay. And so let me run this function just to show you that it's, it does what it said it does. And you can see here's our quadratic function. Okay. And so pretty simple. All right, any questions on this? All right, so question. So why do I put a period after the x in the y equation? Yeah, that's a good question. So, this period right here is used when you want to do element by element operations, okay? And so we want this y, we do that here because we want the y vector to be the entries of the x vector kind of squared, okay? Because MATLAB can also do vector-vector operations. So if you do kind of x times x, what MATLAB will do there is it will actually take the x vector and try to multiply it by the x vector using weird vector multiplication. And so we don't want that. And so what we want here is actually the entries of the x vector to be squared. And so to kind of tell MATLAB that we want to do entry by entry operations, we add that period there. Yeah. Mm-hmm. Yeah, so I guess another way that Evangeline was saying that it's basically a vector to scalar operation. So that's kind of another way that you can think of it as well. Yeah. Right, so there's a question in the chat. So what do we do to plot 2 separate figures? Yeah, that's a good question. And so if we want to plot a second figure, let's say that we have z is equal to x cubed, okay? And say we want to plot z on a different function or a different figure. You can just call the figure function here. And so we can say figure 2. Okay, and we can do plot x comma z. Okay. I won't give it a title here just because I want to demonstrate. And when you run this code, you can see that 2 figures are created here. Okay, and so figure 1 has our quadratic function, and then figure 2 has our cubic function. Okay, and so when you want to create multiple figures in your MATLAB code, you just write down the code figure, and then you give it a unique number. Okay, you don't have to go 1, 2, 3, but for me, that kind of makes the most sense, and it helps me kind of keep track of how many figures that I have. But you can easily just do figure 99 here, and it'll do kind of the same thing. Yeah, so you have figure 99. But for me, I like to start at 1 and just count up, 1, 2, 3, 4 from there. Yeah. All right, question. So you can also hold to add all the graphs to the same graph, right? Yeah, you definitely can. So it's not limited to just 1 line per graph. So actually, you can add multiple lines per graph as well. And so let's say that we want to add the z graph onto this figure 1 here. And so the way that you do that, you can plot multiple things on once. You can use the command called hold on. And so what that'll tell MATLAB is that, I want to put multiple plots on the same figure. Okay. Then you can just call the plot command again. Okay. And so let's say that we're going to plot the next one. Okay. And then after you do hold on, make sure you do hold off, because that will make sure you hold it off. Okay, and you can see right here now we've put 2 plots onto the same figure. Okay, so we have our quadratic function down here, and then we have our cubic function right here. Okay, and when you put multiple plots onto the same figure, then MATLAB will automatically change its color for you. So that's kind of another nice thing in MATLAB as well. Okay. All right, any final questions on this? Okay. All right, so that concludes. Oh, hang on. Do you need to hold on for each new plot? No. So hold on is kind of like a toggle. And so you can actually add multiple plots right here, right? So you can do plot x comma, let's do a fourth order function, okay? And then this will add a third line with only hold on right here, okay? And so you only need to hold on once. It's just that it's kind of like a toggle on and toggle off kind of thing. Yeah. Okay. Okay. And so now let's switch gears, and now let's start going to finite differences. Okay. So let me switch over here. Okay. All right. And so now we're going to start getting into the theory, which is going to drive, our code. Because up to this point, we've mostly just been doing review and kind of just introduction stuff. So we reviewed kind of, the concepts that we need to know from heat transfer and fluids. And now that we've reviewed MATLAB, now we're ready to really kind of start diving into the class itself. Okay. And so our first stop here is going to be, a methodology known as finite difference. And this is something that's going to carry us, throughout the entire first half of the course, okay? Pretty much up until the first midterm, okay? And so today, we're just going to introduce the idea of finite difference and how we can use it to approximate derivatives, okay? So this is kind of the key here is that, we have our differential equation here, and so we need a way to kind of discretize it, okay? Okay, so let's go ahead and get started. So just to kind of start, let me kind of remind you of kind of the general transport equation or the general conservation equation that we're going to be working with in this class, okay? Okay, and so in that equation, we had something like this. We had partial phi, partial t, right? And remember, we use phi here to represent just an arbitrary, variable. And so this phi here could be temperature in heat, but it can also be mass for mass transport, but it can also be velocity for fluids. Okay, and so this is kind of just general transport equation. Okay? And so on the left there, we have our unsteady term and our convective term. And on the right here, I'm writing our diffusion terms. Okay. And so we have our little hangman here. That's going to be our diffusion coefficient. Okay. Okay. And then finally, we have our source term. Okay. And so this is the equation we're going to be working with here. And so, we're not actually going to simulate this yet. But what I wrote this again just to highlight that we have a crap ton of derivatives here, right? And so we have derivatives in time, we have derivatives in space, we have second order derivatives, and so there's a lot going on, okay? And if you remember, ultimately we want the computer to solve this equation for us, but the computer doesn't actually know what to do with derivatives because computer's not that smart. And so what we need to do is the first thing that we need to do before we can code stuff up is to take all the derivatives here and then convert it into an algebraic expression. Okay. And this process of converting a derivative into algebra is known as discretizing the equation. Okay. Okay. And so before we kind of move on, I will say that there's lots of different methods out there that you can use to discretize an equation. Okay, and so we're going to start with one called finite difference. And so for me, when I was learning this stuff, finite difference was the first one that I learned. And personally, I think it's kind of the simplest one to kind of, at least conceptually understand. But there are a lot of other ones out there. And so, later on in the class, we'll learn a method called the finite volume method. Okay. And then another famous one that you've probably heard before is the finite element method. Okay. And so this is kind of like the finite family, right? Maybe not as fun as the Brady Bunch, but they all kind of do the same thing. Okay. So basically, any method that starts with finite, they all kind of do the same thing. Okay. So we're going to start with finite difference, but just know that there's other ones out there. Okay. All right. And so let's go ahead and motivate finite difference. So let me go ahead and draw a plot here. Okay. And so in this plot, let's say that the y-axis will have, we'll say it's labeled by u. Okay. And our x-axis will be the x-axis. Okay. And let's say that we have a function that looks like this. Okay. All right. And so in this case, we don't know the functional form of this function, but we do know where its data points are. So let's say that, on this function right here, we know the value of all of these data points. Okay. And so we'll label these data points, label data point 1, data point 2, data point 3, 4, 5, 6, 7, and then 8. Okay. These data points are selected such that there's an even amount of x spacing in between them. Okay. And so if we kind of project these points back down to the x-axis, right, we can say that the space in between each of these points, the horizontal space, is delta x. Okay. And so that delta x is the same for each one. So the space between 1 and 2 is the same, space between 2 and 3 is the same, and the space between 3 and 4 and so on. Okay. Okay. And so let's say that, we have this function, or we have this graph right here. We don't know its function, but what we want to do is we want to compute the slope of the curve at location 5. Okay. All right. And so normally, like kind of what you would do in your first calculus class is that you would simply take the derivative of the function and then evaluate that derivative at location 5, right? And so that's how you would find slope kind of in the calculus way, right? But in this case, we don't have the functional form, right? Okay. And so we don't have u of x. And so we don't have u as a function of x right here. We only have its data points. Okay. All right. Oh, question in the chat. So last class, did I say we do this because computer programs have an easier time solving linear algebra problems as opposed to partial differential equations? Yes. Yeah. So that's kind of the primary reason we're doing this, is so that we convert this into an algebra problem, and so that the computer has a really good time with it. Yeah. It'll be a really, really big algebra problem, so it wouldn't be something that we could solve, with human capabilities, but a computer would be able to do that. So computers are really good at solving really, really, really big algebra problems, and so that's kind of our goal for a lot of our methods here. Okay. All right. And so since we don't have u of x right here, another way that we can find slope is to kind of go back to kind of our very first, high school understanding of what slope is, right? Slope is nothing more than rise over run, right? And so we can compute, how much the function rises in the vicinity of 0.5 versus, how much it runs, then, we can compute the slope, okay? And we can actually do that because we actually have these locations, right? And so we know both of the x locations of all of these points, and we know the y coordinates too. Okay. Okay. And so this would be like u6, u5, u4. Okay. And so since we have the X and Y coordinates for each one of these points, we can use that information to, compute this rise over run. Okay. Okay. Any questions on this? Okay. All right. So let's go ahead and start computing that. Okay. And so let's start with the rise. Okay. And so, we want to compute how much the function goes up in the vicinity of point number 5. Okay. And so one way that we can do that is we can just take the difference of the y coordinates of locations 6 and 4. Okay. Or 4 and 6, I should say. Okay. And so rise will be u6, which is the y coordinate of location 6, minus u4, which is the y coordinate of location 4. Okay. And so I picked 6 and 4 because, those are the left and right neighbors for location 5 right here. Okay. Yes. So it says y coordinate. Yeah. Coordinate. Yeah. Mm-hmm. Okay. And so that's the rise. And the run is going to be the difference of the x coordinates between location 4 and 6. Okay. Okay. And so the run is going to be x6 minus x4. Okay. And actually, we can simplify this a little bit more because we know that each of the x coordinates are evenly spaced from each other, right? So we know that each x coordinate is separated by delta x, right? And so if we take x6 minus x4, what that's going to get us is 2 delta x, right? Because we know that the space between 4 and 5 is delta x. We know the space between 5 and 6 is going to be delta x. And so if we take 6 minus 4 of just their x coordinates, we're going to get 2 delta x. Okay. Right. And so now that we have the rise and now that we have the run, we can just compute the slope. Okay. And so our slope, okay, is going to be u6 minus u4 divided by 2 delta x. Okay. And this slope right here is also going to be equal to the derivative of the function at location 5. x5, I should say. Okay. Right. And so this result here is really significant because on one side of here, we have, just an expression that has subtractions and divisions and multiplications. And so this is an algebraic expression. Okay. Whereas on the right here, we have a derivative. So this is a, derivative expression. Okay. Okay. And so what we have here is basically a relationship between algebra and calculus. Okay. And this basically forms the basis for finite difference. Okay. And so in finite difference, basically you're gonna be replacing derivatives with these things called finite difference formulas, which is just going to be a difference between or a ratio between rise over run, basically. Okay. And so the general form, and so this is kind of a specific example for location 5, but we can generalize this for any other location. Okay. And this particular finite difference scheme is called the central difference, which we'll touch on in a bit. Okay. And so the general central difference scheme is given by the following. Okay. And so let's say that we have a derivative that looks like this, okay, is going to be evaluated at u I plus 1 minus u I minus 1, okay, all divided by 2 delta x. Okay. And so this is our general formula for a central difference scheme, okay? And so basically you take your function values, which is on the top, and so you find the function value of your right neighbor and your left neighbor. So your right neighbor is given by ui plus 1, and your left neighbor is given by ui minus 1, and then you divide by the horizontal difference, horizontal distance in between them. And so that's usually, you know, if you have an even space grid, that's going to be 2 times delta x, okay? Right. And so this kind of central difference, finite difference scheme can be used to convert between derivatives and algebra, basically, okay? And so what we're going to do is we're going to take, you know, finite difference schemes like this and plug it back into our general conservation equation in order to convert that kind of big monstrous guy into, you know, a big monstrous algebraic system, okay? Okay, any questions on this? Okay. Okay. And so, you know, I mentioned just previously that formula back there is called a central difference. And so, you know, that's, you know, that kind of alludes to the fact that there might be other finite difference schemes out there. Okay. And so here's some other 2 popular finite difference schemes. Okay. Okay. And in particular, these are for first order derivatives. Okay. And so the first one we'll go over is the forward difference. Okay. And so the forward difference is given by this formula here. So we have u I plus 1 minus ui all divided by delta x, okay? And this is equal to du dx, okay? Okay. And so another popular formula is the backward difference. And so the formula for that is going to be u I minus ui minus 1 all divided by delta x. Okay. And so this is again equal to du dx. Okay. Okay. And so there's we have 3 different ways here that we can approximate a first order derivative. So we have a central difference, we have a forward difference, and we have a backward difference. Okay. Okay. And so, you know, logically speaking, you can see how all of these, they all kind of represent the same thing. So they represent a way to compute rise over run in a discretized sense. Okay. And so now the question is, you know, we have all of these 3 expressions and they all look fine. Okay. And they are fine, you know, you can use them. But now, you know, how do we, you know, how are they different and how do we choose which one to use? Okay. And so I use sometimes I'll use the acronym FD, and FD stands for finite difference. Okay. Okay. And so one way that we can tell them apart is to compute how accurate they are. Okay. 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 Because remember, whenever we perform any kind of discretization, we're going to be incurring some kind of errors, because a discretization is never going to be the same accuracy as reality, right? And so you can think about it, you take an image and you pixelate it, right? It doesn't matter how fine you pixelate it, a pixelization is still a pixelization, right? And so same thing for here, okay? And so the way that we actually assess accuracy is to use a Taylor series expansion, right? And so I know that that's something that you probably have. It might be a suppressed memory from back, from your early math classes, but it's actually really useful here for us to determine accuracy. And it's going to be a little bit scary, but trust me, it's okay. Okay, and so let's do a Taylor series expansion of each of the terms here. Okay. I swear, I think the first time I learned finite difference, and then my my professor said, we're going to do a Taylor series. Like in the back of my mind, I could hear my first calculus college professor just cackling in the back of my head, and it was not a pleasant sight. Yeah. Okay, and so let's do a Taylor series expansion of ui plus 1. Okay. Okay. So let's do ui plus 1. Okay. I'm going to write it down in a different form because this will help us with the Taylor series, and so this will be u at x plus delta x. Okay, because remember, ui plus 1 basically means that we're moving on to our right neighbor, and so our right neighbor is going to be located at x plus delta x. Okay, so we just move one location over, right? And so the Taylor series expansion of this looks like this. So we're going to have u of x plus du dx. Okay. And so here's our first order derivative term for the Taylor series times delta x. Okay. Plus our second order derivative term, which is going to be d squared u dx squared times delta x squared divided by 2. Okay. And then, of course, this continues onwards, but for this, we're only going to use just these terms right here. So we're going to do dot plus dot dot dot. Okay. And so we just have this expansion here among these terms right here. Okay. And so what this basically says is that an approximate way to express the value of the function at u at x plus delta x is to take the value of the function at x, and so that's what we have here, u of x, plus the derivative of the function multiplied by the spacing, plus the second derivative of the function times the spacing squared divided by 2. Okay, and so if you check the units for all of these have the same units of u, and they have different powers of delta x that kind of cancel out the derivative terms. Yeah. Taylor Swift, Taylor Lautner, lots of Taylors out there. Yeah. Okay. And so from here, we can basically use this to, we're going to manipulate this a little bit to use it to determine accuracy. Okay. But this right here, this is just, a Taylor series expansion of this guy. Okay. So any questions on this before I move on? Okay. All right. So we're going to manipulate this expression here a little bit. Okay. And so the way we're going to manipulate it, I'm going to do two operations. First thing, I'm going to subtract u of x from both sides. Okay, so that's the first thing I'm going to do. And then the next thing I'm going to do is I'm going to divide the entire expression by delta x. Okay. And so what that'll do, the reason I'm doing this is because I want to kind of isolate this this guy right here. Okay. Because remember, we're using these finite difference schemes to approximate this first order derivative. Yeah. All right, question. So this is an approximation, right? So what about using other computational methods like Runge-Kutta? Yeah, so that's a good question. So yeah, this is just an approximation. And then the RK method that you're talking about is going to be more for time integration actually. And so that's something we're going to discuss more once we start doing unsteady stuff. But this is strictly just for the time derivative, or for the space derivative. Sorry. Yeah. For this class, I don't think we're going to have enough time to go into Rangukata, although it's a method I really like. And so we're just going to stick with Euler and implicit Euler basically. Yeah. Right. Yes. So right. So we want to get the first order derivative by itself because that's what we're approximating, right? And so we're basically using this Taylor series to have an idea of what's the accuracy of this du dx that we're trying to approximate. Yeah. Okay. So let's go ahead and do that. And so after I perform those two operations there, we're going to have u at delta x, or x plus delta x minus u of x. Okay. Divided by delta x. Okay. This is equal to du dx plus d squared u dx squared delta x over 2. Okay. And so this d squared u dx squared, it normally had a delta x squared, but since we divide by delta x, that cancels one of the terms on top. Okay. Okay. And so I want to draw your attention to this term right here. Okay. Because another way that we can write this term is ui plus 1 minus ui, okay, all divided by delta x, okay? And we'll rewrite these guys down again. So this can be du dx plus d squared u dx squared delta x over 2, okay? And so this guy right here, this is our forward difference scheme. Okay. And then now what we're going to do is we're going to take this guy and then we're going to move it over to that side of the equation, okay? And so once we do that, we get our forward difference scheme. So we're going to have ui plus 1 minus ui over delta x minus d squared u dx squared times delta x over 2 is equal to du dx. Okay. And so this expression here is believe it or not, is an expression of the accuracy, right? Because remember when we started doing this finite difference, we wanted our algebraic expression, which I have here. We want this to be exactly this, right? And so we ultimately want both those two terms in orange to be the same as each other. But we see that when we do a Taylor series expansion, they're not exactly equal. And the difference in between them is this guy, right? And so this is the guy that's kind of uninvited to the party, right? And so this is kind of our what I call our leading error term. Okay. Because this guy is the only thing that's preventing our forward difference scheme to be equal to our derivative, which is what we want, right? But because we did our Taylor series expansion, we saw that there's an extra guy here. Okay, and in reality, there's actually a lot of extra terms if you keep expanding the the Taylor series. Remember, the Taylor series we only stopped at the second order term, but this is the only one that really matters because it's the leading error term. Okay. Okay, and so the thing that I want to highlight most here is the derivative actually is actually not that important. We don't have to worry about that. And so the thing that I want to draw your attention to is actually this guy, okay? And in fact, the what I want to highlight is the power of delta x that this is, okay? And so this is delta x over 2. And so it's basically delta x to the first power. And so this tells us that this forward difference scheme, we call it first order accurate. And so what that means is that the leading error term for forward difference is delta x to the first power. Okay. Okay. And so, practically what this means is that, if we're using a forward difference and we want to reduce the error, what we can do is we can just make delta x smaller. Right? And so if we make delta x smaller, then we minimize the error and everyone's happy, right? And so the fact that this is delta x to the first power means that if we, the error will go down basically exactly as we reduce the grid size. And so if we reduce, the grid spacing, that's what delta x is, by a factor of 2, then our error will also go down by a factor of 2 as well. Okay. And so that's what it means to be first order accurate. To be first order accurate means that, any change that you make in the grid size, you're going to see an exact same change in the error as well. Okay. Okay. Any questions on this? Okay. And so now we've established that the forward difference scheme is first order accurate. Now let's look at our other two. So let's look at our backward difference scheme just really quickly. Okay. And for our backward difference, we're going to do a Taylor series expansion around ui minus 1. Okay. And so to do that, we have ui minus 1 is equal to u at x minus delta x. Okay. And this is equal to u of x minus du dx delta x plus d squared u dx squared delta x squared divided by 2. Okay. Right. And so we can do the same thing here. So we're going to try to isolate du dx. And since most of the algebraic steps are mostly the same, I'm just going to go ahead and skip to the results. Okay. And so what we get for this one is that du dx is equal to ux minus ux minus delta x, okay, divided by delta x. And so that's our backward difference scheme. And it's going to be plus d squared u dx squared delta x over 2. Okay. And so once again, we have our leading error term. Okay. And once again, we see that we have delta x raised to the first power. And so this tells us that backward difference is also first order accurate. Okay. Okay. And so both forward and backward difference are first order accurate. Okay. And so in terms of kind of absolute sense, first order accurate is fine. And so it's better than not being accurate, but it's not the best. So usually you want to do something a little bit better than that. Okay. And so for something a little bit better, let's go back and check our central difference. Okay. Okay. And so remember, our central difference scheme was given by the following. My stylus will cooperate. Okay. And so we have ui plus 1 minus ui minus 1, all divided by 2 delta x. Okay. And so we're saying that this is an approximation for du dx. Okay. And so we can do the same thing here, where we can use Taylor series to compute its accuracy. Okay. But the way that we can do that for a central difference is we can take the difference between the Taylor series of ui plus 1 and ui minus 1. Okay. Okay. Okay, and so we're basically going to take, this guy up here and then subtract it from the other one, okay? And, we're going to do the same exercise where we isolate du dx, okay? And so, if you want to kind of find, see the work for this, you can check in the notes, but I'm just going to go ahead and skip to the result, okay? And so if you do this and you isolate our central difference scheme, you get the following. Okay? And so you get du dx is equal to ui plus 1 minus ui minus 1 divided by 2 delta x, okay? And so there's our, the derivative that we want to approximate and our central difference scheme. And then we have our leading error term, okay? And so I didn't want to write this out because we need to actually go up to the third derivative here. And so we see d cubed u dx cubed times delta x squared divided by 6, okay? And so here is our leading error term. Okay, and you can see here it has x squared, right? And so that x squared tells us that the central difference scheme is second order accurate, okay? And second order accurate is better than first order accurate, right? Okay, any questions on this? Okay, all right. And so let's talk about being second order accurate for a second. Okay. Right. And so second order accurate means that the error is going to go down according to the grid spacing squared. Okay. Okay. And so basically one way that you can say this is you can say that error is approximately equal to x squared, okay? And so let's do an example to kind of give you a sense of how much more quickly the error can go down in second order, okay? Right. And so let's say that we run a finite difference simulation, but then we run a second one where the grid spacing is half of what it was before, okay? So we're going to have the grid spacing. Okay. And we'll say that, delta x nu is equal to delta x divided by 2. Okay. And so let's plug in delta x divided by 2 up here, right? So we're going to have error is equal to delta x divided by 2 squared. Okay. And so we work this out. And we say that error is going to be delta x squared divided by 4, okay? All right, so the key here is the divide by 4, right? And so we took our grid spacing and we divided by 2, but by doing that, we've actually reduced our error by a factor of 4, okay? And so this is nice because now, whenever we reduce the grid spacing, we get much more bang for our buck here because our error is going down much faster than our grid spacing is going down. So that's actually really, really nice. Okay. Okay. All right. And so, the higher order accuracy, generally is better because, you're going to have a more accurate solution. But once you get past second order, what tends to happen is if you want higher order accuracy, you're going to have to do a lot more work to do that, right? And so central difference is really nice because we only need to use two terms in it, right? So we only needed ui plus 1 and ui minus 1, right? But if you want to go to third order accurate or fourth order accurate, you're going to need to start including more terms. So like 3 terms, 4 terms, 5 terms, and that's when things start to become kind of a mess. And so second order accurate, just kind of practically speaking, is kind of a good place to be because it's kind of a good balance between like, you have pretty good accuracy, but then your finite difference expressions don't get crazy, okay? And so, actually a lot of, practical research codes, commercial codes, a lot of times what they aim for actually is second order accurate. And that's usually pretty good in most people's book, okay? Okay, and so everything we've talked about so far is first order derivatives, but we can find a finite difference scheme for a second order derivative as well, okay? All right, so our second order derivative is going to be d squared u dx squared, okay? And then the finite difference approximation looks like this, okay? So it's going to be ui plus 1 minus 2ui, okay, plus ui minus 1 all over delta x squared, okay? Right. And so you can see it uses 3 terms. So it uses both the right neighbor, it uses the value for itself, and also its left neighbor as well, okay? And you can see at the bottom here, we have delta x squared because it's a second order derivative, okay? All right, so for second order derivatives, we're only going to work with this one just because this is kind of the best one you can do. And the accuracy for this guy is second order accurate. Okay. Right. And so this scheme right here is really popular just because it's it's not that complicated because it's only 3 terms and it gets you to second order accurate, which is kind of the magic threshold that everyone wants to be, right? Okay. All right, so I won't go through the Taylor series for this because I think that's kind of enough for one day. It's enough for me too. So, but if you wanted to verify that this is second order accurate, you can go through the same exercise as what we did previously. So you Taylor expand ui plus 1, you do a Taylor expansion of ui minus 1, you manipulate them such that you get this expression, and then you look at the the order of delta x on the leading error term. Okay. Okay. Any questions on this? Okay. All right. And so that's first order derivatives and second order derivatives. But let's talk about 2D stuff just briefly. Okay. Right. Because eventually what we're going to do is we're going to do work with 2D problems, and the same methodology here is going to apply. Okay. Right. And so let's say that we have a 2D grid. Okay. And so let's say that we have a location here, and its coordinates are I, j, okay? And then next to this, we have its 4 neighbors, okay? And so we have its upper neighbor, we have its lower neighbor, its left neighbor, and its right neighbor, okay? And the coordinates for each of these guys will be I, j plus 1 for the upper neighbor. Then lower neighbor will be I, j minus 1, okay? The right neighbor will be I plus 1, comma, j, and the left neighbor will be I minus 1, comma, j. Okay. Okay. And so we can form all the partial derivatives of u in this case too. Okay. So let's do partial u, partial x. Okay. And so if we want to compute the x derivatives, we're going to use the neighbors in the x direction. So the left neighbor and the right neighbor. Okay. So this is going to be u, I plus 1, comma, j, minus ui minus 1, comma, j, I'll divide by 2 delta x, okay? And so delta x would be this distance right here, okay? And then we also have this vertical distance here would be delta y, okay? And then similarly, you can have the partial derivative in the y direction. So partial u partial y is going to be equal to, finite difference expression, but now we're using the upper and lower neighbors. So this is going to be ui j plus 1 minus u I j minus 1, okay, all divided by 2 delta y, okay? Okay. And then we can have our second derivatives too. So let me just write down one just for completeness. Okay. And so if we have the second derivative of u with respect to x, okay, we can have u I plus 1 comma j minus 2 u I comma j plus u I minus 1 comma j, okay, all divided by delta x squared, okay. And then you can use the same expression for the y derivative as well, okay. Okay. And so, just because we're in 2D, we can still use the same finite difference schemes. The only thing is, you have to make sure you use the right neighbors and you use the right grid spacing in that direction, okay. And so, when you start getting into 2D, the question, of course, is, can you have also mixed derivatives as well? And you can. So you can have partial squared u, partial x, partial y, okay? And so that's definitely possible. But, we're lucky in the sense that heat transfer problems and, fluid problems, they very rarely have these mixed derivatives. So we're just not going to consider them in this class just because, we just almost never see them. But you can come up with the finite difference schemes for those as well. Okay. Okay. Any questions on this? Okay. And so the last thing I want to talk about, which I think we'll have to finish up on Monday, is discussing what kinds of errors that you can have in these kinds of computational simulation. Okay. Because anytime you do any kind of computational engineering, kind of the name of the game is to kind of minimize your errors as much as possible. Right? All right, so question, will we see more heat transfer problems next week? So starting here, we're going to start to kind of break down our general conservation equation. So we're going to be a little bit detached from the application. So, I just kind of want to warn you guys right now, because we need to kind of, dive a lot into the theory. And so, for the next couple of weeks, it's going to be a little bit heavy on the theory and a little bit heavy on the math. But, once we start to get those out of the way, then we'll apply this kind of, heat transfer problems. Yeah. Yeah. It's going to be a little bit, it's going to be a little intense. It's going to be a lot of theory and a lot of MATLAB programming and a lot of math, but, it'll eventually lead us back to the applications. Yeah, so you kind of almost think of today as kind of almost like an appetizer for, a lot of what's to come over the next few weeks. Okay. So errors. And so, whenever we, are doing any kind of computational simulation, the name of the game is to always kind of minimize the errors as much as possible, because you want your simulation to match reality, right? And so to do that, you can minimize the errors. And so in order to best do that, it's always good to kind of understand, where exactly are your errors coming from and how exactly do you reduce them, okay? Okay, and so the first type of error that I want to talk about is called truncation error. Okay. And so truncation error has to do with the fact that, we're making this finite difference approximation that we've talked about today, okay? And so these are errors associated with discretizing the equation. Okay. And so the fact that we went from something like a derivative expression like this, and so the fact that we went from du dx and we approximated it using like a finite difference, And so the fact that we did this, we're going to incur some errors about that with this, right? And so that's all the errors that we talked about with the Taylor series expansion, okay? And so the reason these are called truncation errors is you can kind of think of it as these are errors that are associated with truncating the Taylor series, right? And so when we did our Taylor series expansions for all of these different U terms, you saw that, the Taylor series expansion went on and on. But for the most part, we're just ignoring the fact that all the other Taylor series stuff was there. And so we're just kind of truncating it at just the stuff that we care about, okay? And so since we're truncating that Taylor series expansion, we're going to incur some errors, and that's what this truncation error might be, okay? Okay. All right, and so the next thing I want to, next error that we can have is called round-off errors. And so these errors are associated with the fact that your computer can only represent numbers using a finite number of precision, okay? Okay. And so let's say that, you have kind of a particularly nasty irrational number that looks something like this. Okay. So let's say that we have 4.2367943112567 8, and it kind of continues on forever, right? And so you have basically a decimal that just continues on, right? At some point, because your computer just can't store an infinite amount of numbers, it's going to have to cut this off at some point, right? And so some popular places are after 8 decimal points or after 16 decimal points. 1, 2, 3, 4, 5, 6, 7, 8. I missed it by 1. Okay. And so the fact that, we have to cut off decimals like this means that we're going to, incur some error there as well. Okay. Right. Okay. So the question in the chat is, what's the difference between truncation and rounding? And so truncation error comes from the fact that, we're actually not computing exact derivatives in our code. We're doing kind of algebraic representations of derivatives. Okay. And so, what we hope is that these algebraic representations are good representations, but they're never going to be exactly the same as a derivative. And so truncation error has to do with the fact that, we're taking a derivative, which is kind of a continuous thing, and we're approximating it with kind of a discrete algebraic expression. So that's truncation. And so round-off errors have to do with the fact that, when you actually compute things in your computer and in your calculator too, you have to cut the decimals off at a certain point. You can't just keep decimals going on forever. Because, in order to actually store all those numbers, you need to actually have memory for them. And the computer usually doesn't have that. Yeah. Right. Yes. And Juan brought up a good point too. And some computational methods will actually cut these off sooner to save time, because actually even saving up to 8 decimal points can be kind of a chore as well. Yeah. Okay. And so it might seem pretty insignificant, but when you cut off things at the 8th decimal, it's like, who cares? We got the first 7, right? But what if you can imagine, your computer is doing billions and billions of these calculations, and if you have these round-off errors, eventually those round-off errors are going to be significant, right? And so by themselves, round-off errors are actually no one really cares, but for when you combine them together with billions and billions of calculations, that's when things, the errors kind of start to accumulate. Yeah. Okay. All right. So any final questions on this? Okay. So that's all we got time for this week. So thank you everyone for tuning in as usual. And so when we pick this up again on Monday, there's a couple more errors that I want to talk about. And then we'll actually start to, work with some differential equations and actually simulate them in MATLAB. So make sure you have MATLAB ready for next week because we're going to be doing some activities in class. Right? And so hope everyone has a good evening. Hope everyone has a good weekend. Let me know if you have any questions on the homework, and I'll see you guys on Monday.
Professor.
Hi.
I have a question on problem 2 on the homework.
Yep. Mm-hmm.
it says write down the corresponding matrix form. Do you mean like by hand?
Yes.
Okay,
Yes.
okay. Just making sure.
Mhm.
Thank you.
Yeah. Thanks, everybody.
Wait, Professor?
Yep.
Was that homework 1 she was referring to?
Yeah, homework 1. Yeah.
We're supposed to do it by hand?
So when you do the matrix or system of equations, it'd be nice to have the matrix form if you have it by hand, but if you have it in the code, that's okay too. As long as I can see that you took the system of equations and did it and put it, in matrix form, then that's fine.
Okay.
So by hand is kind of, usually a lot of people start with that, but if you want to just insert it directly in the code, that's fine too.
All right, thank you.
Yeah.
So when we turn it in, what I did was I made a Word doc for problem 1, and then the code, I did it for the rest of them. Is that okay? Can we submit more than one file?
Yeah, you can submit more than one file. So I think Canvas should accept both. I think it accepts PDFs. I set it to accept PDFs and MATLAB files.
Okay, well, good to know. Thank you.
Yep.
Python file.
Oh, okay. Yeah, I have to allow it to. I have to change it to allow Python file. So let me do that after the lecture today.
I haven't submitted yet, but you've already seen it.
Yeah. I mean, the PDF you sent me looked fine too.
Oh, okay.
Yeah.
All right.
All right. So if you write it down digitally, that's fine too. So if you if you just write it down digitally and save it as a PDF, then that's perfect too. As long as I can read it and I can understand what you're doing, that's all that I care about.